So when we look at the sky, we typically can see these type of images that are really, really pretty and colorful and show a lot of stars. And I think now, we're all in the Netherlands and it's spring. And this may remind you of something else that is really pretty and colorful, and that is a field of tulips. And so today I would like to present to you Tulips, a tool for understanding the lives, interiors, and physics of stars. So for those of you who may not know me, I'm Eva Laplace. I'm a third-year PhD student here at API. My supervisors are Selma de Mink and Stephen Justham. And I work on stellar astrophysics. So just some brief words on my research. So my research is about massive stars that don't live alone, but have a companion. These are massive binary stars. And I'm specifically interested in the stars that are more massive than their companion to begin with, and that will interact with their companion and lose matter by transferring this matter to the companion star. What I'm mainly interested in is how these stars evolve and how these stars die. So their properties at the moment of explosion, and also what they leave behind, and what the consequences are for gravitational wave sources. So I work in the field of stellar evolution, and this is all based on something that is called stellar evolution theory. Yeah, and I think this can be summarized really well by this sentence of the lecture notes of Anna Pauls that you may be familiar with. And so stellar evolution theory is about understanding the structure and evolution of stars and their observational properties using known laws of physics. And what is really interesting and amazing about this is that you need physics from the smallest scales and from the larger scales to describe the evolution of stars. So you need lots of ingredients like mechanics, thermodynamics, nuclear physics, quantum mechanics, all of this together makes stellar evolution theory. And so it's a little bit complex because of this, but it can be described beautifully in quite a simple form. And it has been, it has experienced a major development in the last half century. And it is also one of the first problems that was successfully simulated with computers. So the picture that you see here is Rudolf Kippenhahn, this person here, and some of his collaborators working on one of the first computers that were solving the evolution of stars. And stellar evolution theory has a long history, but it's still really relevant today. And I think it has never been as relevant as now. And I think we're now seeing quite a renaissance in stellar evolution after it was disregarded for some time. And that is because it is essential for addressing big questions that we are currently being able to solve much better than before. And that is, how do stars evolve? How do stars die? What do they leave behind? Kind of compact objects like neutron stars, black holes, white dwarfs, all of that. And also, what about binaries? And something that is really timely now is, what about gravitational wave progenitors? Where do they come from? And the thing is, so stellar evolution theory is really important, but it also has this thing that it is really marked by history. So you all know this, right? In astronomy, you not only have to learn the physics, but you have to learn all the history and the interesting way we name things and we show things to actually grasp what's going on. And this is a major difficulty. So I've been teaching as a teaching assistant the class Stellar Structure and Evolution for 3 years now. And I can tell you it's always a challenge to make people understand what's actually going on. And this can be, I think, really well illustrated with this diagram here that we all love and know really well. So it's, of course, a color magnitude diagram, or also luminosity temperature diagram, also known as the Hertzsprung-Russell diagram, that has this amazing property of summarizing all the very important essential information about stars. And now we all know this, right? So we are familiar with how we plot this, how we talk about this. But if we just take a step back and just remember how it was when we were students, or remember how it is for new students, if you see this, how extremely confusing it is. So what is shown here is 4 million stars observed by the Gaia survey, and where they lie on this temperature luminosity plane or color magnitude plane. And you can see the magnitude, right? Instead of having the numbers going up, well, we all know it goes down, right? And also here, this color information, what is this supposed to mean? We also have this helpful designation of types of stars using their spectra that makes absolutely no sense, right? You have to learn it by heart using a sentence to actually be able to remember what type of star is what. So O stars are hotter than M stars. And also the temperature is really hot on the left side of the diagram, really cool on the right side of the diagram, which is super counterintuitive. And to make everything even easier, everything is shown in a logarithmic scale. That is absolutely not intuitive to most people when they first see this. Okay, so the idea here is to make this a little bit easier for people to understand. So the core idea here is of what I did is to make stellar evolution theory a little bit more accessible and understandable. So, and that is try to find a way to visualize the physical properties of stars in a more intuitive way. And if possible, base this on latest theoretical simulations, because we have all these things available now. So how did I do this? So the basic concept is really simple, and I'm sure you all know this. And that is a trick that is very commonly used in physics. So typically, how we show the change of a property is we plot quantity x on the y-axis, and we show how it changes as a function of time, or mass, or radius, or something. And then you have to do an to visualize this in your head of what this means for what it's doing inside the star. Okay. And so now, instead of having this step of visualizing this in your head, the idea is to visualize it directly. So how do you do this? You just use what is called Lagrangian coordinates, and you make use of the fact that for many, many problems in stellar astrophysics, and all of the ones that I will talk about here, you can assume that stars are spherical. This is really, really useful, because then you can use spherical symmetry. And this means that you can represent any 1D quantity as the radius of a circle. It's as simple as that, okay? So basically, if you have the radius of a star, instead of showing its evolution, radius here, time here, and you have to imagine in your head what this means for the star, well, you will have a circle, and its radius is the radius of the star. So you can actually see a circle change in size, and I think that's much more intuitive than having to translate this in your head. And this is a very, very simple example, but we can go further. and do more interesting things. And of course, what is really cool with theoretical simulations is that we can know everything that's happening inside the star too. That's something you can't do with observations unless you have neutrino detectors or something. And so, for example, you can use what is called the mass coordinate. So basically, at the center of the star, mass is 0, and then every circle inside the star has a mass of m, okay? And so that means at the surface of the star, the mass is equal to the total mass of the star. That's the basic concept. It's as easy as that. So what is it based on? It is based on these theoretical simulations I was already talking about. And that is called Mesa, the Modules for Experiments in Stellar Astrophysics. So many of you, I'm sure, have heard about this, but I'm just going to recap just in case. So what is Mesa and why is everybody always talking about this? Well, Mesa is a 1D stellar evolution code. So it does assume spherical symmetry. And it is the only open source and community maintained code that is actively developed right now. And it can compute anything from planets, stars, compact objects, binaries, explosions, you name it. And it's getting better every day. And it's very, very popular and has now a community of about 1,000 astronomers. That's a very, very large number. So let me introduce you to Tulips. So this is a Python package, and this is what it can do. So in summary, Tulips can help you visualize the size and actual color of stars. It can help you visualize the burning and mixing processes inside stars. You can compare stars with different properties. And another cool thing you can do is to visualize the composition of stars in a really simple way. So it's a Python package. I'm still developing it, but it will be open source at some point, free, and hopefully also easy to use. It's pretty fast. That basically depends on the Mesa simulation it's based on. You're trying to load. And how does it work? So it's really simple. There's 2 steps. So you need a Mesa model. You need to have run a Mesa model or have found a Mesa model somewhere on the internet. And you use the output file. And that is loaded using this really useful Python package that was developed by Rob Farmer, who is a postdoc here in Amsterdam. And it can create these cool plots here, for example. And so the second step is that you just call the function that you want to create the plot or movie that you want. And that's it, you're done. That's these few lines of codes here. That's all. Okay. So typically, here we have our beloved temperature luminosity diagram again. Typically, the way we show the evolution of a star is like this. This is a 10 solar mass star. I like massive stars, so I'm only going to show you massive stars here. I'm a little bit biased, but it can do any star or even planets if you want. And so typically, you have this gray track here, and that shows you the evolution of the star. So it starts here. The star is burning hydrogen into helium on the main sequence, then leaves the main sequence, becomes a red supergiant, and dies here in a supernova explosion due to core collapse. And maybe that is not so easy to visualize in your head what this means for how the star actually changes in size and how it changes in color. So here's the basic plot that you can make, with Tulips. So just to introduce this to you, this is the most basic one that it can do. basically you have the circle I was talking about, yeah? And the radius of this circle gives you the radius of the star. Yeah, very simple. You may notice that it's a logarithmic scale because, you know, stars tend to get really, really big, up to 1000 solar radii or something. So we have to use logarithmic scale. And the color, I think that's pretty cool, shows you the color of the star as it would appear to the human eye if you were in space and you would just look at it. Okay, so let's look at what I mean by that. I just started a movie. Can you see it? Great, thank you. So this is how a tulip movie looks like. So on the left here, you have an inset temperature luminosity diagram again, just to help you visualize what's going on. And the yellow dot indicates where the point in time where the star is right now. And then you're going to see it evolve. I'm not going to comment on what's happening here because I already explained it. And you can see how the star changes in color and in size and becomes what is called a red supergiant at the moment of its death. And then now you may notice I said red supergiant, but this thing looked orange, right? Okay, why is that? It's because we are biased, because we live on Earth. There's this thing called the atmosphere, and there's Rayleigh scattering going on there. And that means that the light that hits the atmosphere is deflected some bit. And that means everything is shifted to bluer wavelengths. So everything you see here, so for example, the sun appears something like yellow, red, or something like that on Earth, depending on your altitude. But from space, you can see that the sun is not yellow, it's white, right? Okay, just fun fact. Okay. Another thing we can do now is to look at the interior burning inside a star. So I'm just going to introduce that to you very quickly. So how does this work? You have the same kind of diagram, but this time on the radius of the circle is not the radius of the star any longer, but it is the mass of the star. So this is at the beginning of its evolution, so it's 10.5 solar masses to begin with. And because these massive stars lose mass due to winds, you will see that the star will shrink, okay? And then you have probably already noticed this funny color here, yeah? So this color is a summary of it's an average of the energy generation and loss inside the star. So what do I mean by that? So basically, here, to keep it simple, I have divided the star into 40 zones. And for each zone, you can find out what the average energy loss or generation is. And that is given by this color scale. So that means red means you have a lot of energy generation. That's what is dominating in this layer. And purple means that you have a lot of energy losses, for example, due to neutrino emission or something like that. And this will change the color, okay? I hope this is clear. So let's look at how this looks like in a movie. So that's the main sequence. You can see how the star, how it shrunk during the main sequence. Now you have this really, really fast phase on the diagram that is hydrogen shell burning. And you can really see that a star is burning hydrogen in a shell, right? I think that's pretty nice. And then you start helium core burning and all these other core burning processes. And you may have noticed that the star started to shrink due to heavy mass loss as a giant star. And you have more and more and more processes inside the star, inside the core, And at the end, it's dominated by energy losses due to a very strong neutrino emission. And at the end, you can really understand why stars die, why stars like this tend to collapse and explode. And that is because you have so much energy loss from the inside of the star in the very inner core that you cannot sustain the core any longer. It has to collapse, and then you have what is called a core collapse supernova. Okay, so now let me talk to you about the composition of stars, because the diagrams I showed to you before are not so completely novel. So there have been these kind of sketches and diagrams in typical books of stellar evolution before. I don't think there is any based on detailed stellar evolution models, but it is nothing very novel. What I want to introduce you to now is a way to show the composition of stars. So if you Google stellar evolution, one of the first hits is going to be this very famous, I think, Wikipedia page called Stellar Evolution that you may have encountered during your studies at some point. And you will see this thing here. What is this? This is how Wikipedia thinks a massive star looks like at the end of its life. So, spoiler alert, this is not how massive stars look like at the end of their life. I wish nature was that simple, but that's not how it works. So let's just keep that in mind and then see compared to the models that I will show you. Okay. So let me introduce you to a new type of plot. It's still work in progress, okay? So it's not everything is perfect yet, but I think the basic idea is there. So this plot here is showing you the composition of the star, showing all relevant isotopes that are contributing the most to the composition of the star. How does this work? So it's a similar fashion as the diagrams that I showed you before, but it's a tiny bit more complicated. And that is because every ring you see in here, so these are actually 300 rings. You can't see it because it's really tiny. But each ring is a pie chart. And this pie chart tells you how much of the star is composed of which element. So you can see in the outer layers, well, actually here for the entire star, more or less, you can see that a quarter is made of this dark blue stuff, and the rest, more or less, is made of this light blue stuff. And that is, of course, helium and hydrogen. And that is a typical solar metallicity star. Solar metallicity typically means, okay, 25% of your star is helium to begin with. And now the way this is plotted is a little bit more, is a little bit different from the plots I showed you before. So instead of having simply the mass coordinate here, what I have done is to use the square root of the mass coordinate. And this means that the area that you see on this circle is exactly proportional to the fraction of the element inside the star. So that means if you look at this star and you see, oh, there is a quarter of this dark blue stuff, it actually means that a quarter of the star is made of helium. Yeah, I hope this is clear. Okay. And now let's watch a movie. I'm not going to comment because there's a lot of things going on, but I just think it's really cool to see. So the evolution of a star in terms of composition is definitely much, much more complicated than having one onion layer above another onion layer. And this is how it looks like. So it's not a clock, right? It's a star. And maybe you notice this spiral structure here. And for those of you who are familiar with this, this is due to core overshooting and to the core shrinking. Okay, now we have helium burning, carbon burning, soon starting. I know this helium shell burning, carbon burning. And then things become more interesting and more interesting. Lots of things going on in there. Okay, this is massive stars. You have just seen the evolution of the composition of a massive star until core oxygen depletion. So just as a reminder, the traditional way of looking at this is this figure. It's probably one of the most cited papers in astrophysics. This is how we typically picture the composition of a star at one point in time. And I hope that I have convinced you that these plots you can make with tulips are maybe a little bit more understandable. So I'm not sure if you can see this because it's probably really tiny on your screen, but there's this line that is called iron. Okay, I'm just gonna trace it for you. It's there. Yeah, keep that in mind. This is important. I will come back to that later. So here, just a very brief detour to what I'm working on. So I'm working on, right now, I'm trying to understand the difference between how single stars die and how stars that are exactly the same to begin with die when they interacted with a companion and became a strip star. And I call this project How Being Single or in a Couple Affects the Death of Massive Stars. Okay, let's see if it ends up on a paper. I'm trying to convince my supervisors. Okay. And here, this is the structure of a massive star at death from this project. And I think I can securely claim that this is one of the probably best resolved simulations of the evolution of a massive star until the end of its life. And to compute this, I used a nuclear network consisting of 128 isotopes. So what does that mean? That means there is all these reactions going on, all these fusion reactions inside the core of a star. And instead of ignoring most of them and just looking at the most prominent reactions, I looked at all the 128 most important isotopes that are involved in any kind of reaction with each other. And that means, in computational time, this means it took about a month to run these models on a cluster to get to this very well resolved structure. So I'm sure there's a better way to show this, but for now, it is still work in progress. I'm showing you all the list of elements and their color like this on this list. And I think you have seen before, so I noted before this iron thing, right? Well, iron is not iron. Okay, that's a point I want to make here. The inner core of a star is so much more complex and diverse than just iron. So it's made of all of these beautiful isotopes, and you can see this interesting spiral pattern here of all these different iron group elements inside the star. And I think this is really exciting because we have, I think, to my knowledge, we have never been able to picture this before because there's just too many elements. You can't plot them all. And also people have not computed it this way because it's too expensive. Okay, so I'm excited about this. Yeah, and another thing you can do is to try to compare the structure of single stars to the structure of binary stars, the thing I was talking to you about. And you may notice that just as a quick glance, these are pretty different. And not only because the strip stars are missing this light blue stuff that is hydrogen, but also their composition structure is different intrinsically. And that's very, very interesting. So I'm working on that, but more on this later in the year, I hope. Okay. So how can this be applied? How can tulips be applied? I think a good example is teaching. So I've made a first experiment during the course taught by Henny Lammers in this winter. So during the last tutorial class, I've shown some of these movies from Tulips, and I think it was helpful for the understanding of stellar evolution theory for the students. Some of you might be in the audience, so just feel free to give me feedback on that. And that was together with my colleague Ines. And it's currently also taught in Harvard by Selma Demik. So this is a picture of a class from last week. You can see Lieke van Son and Selma, and how they explain the evolution of a one solar mass star to their students. I think it's maybe it's another type of star. Anyway, I think it's cool that it's being used already. Okay, so of course, there's still work in progress. There's still many things to do. So there are a few items on my list, and that is that I can expand this concept of visualizing stellar evolution in this way for doing many other things. So for example, you can visualize binary interaction. You can have more information on the fusion processes as it's going on in the star. And in general, I want to improve the code because I want other people to be able to use it. And also another thing I would like to do is to create Jupyter notebooks and also sample movies, so that maybe teachers and people who are less familiar with coding can also make use of these simulations and of the capabilities of Tulips. And yeah, of course, another goal is to publish the code at some point, and also to write an article about it, because I think it would be good to advertise it and to explain it to the community. So to conclude, I have introduced you to Tulips, the tool for understanding the lives, interiors, and physics of stars. So Tulips is a new Python package to visualize the structure and evolution of stars, and is based on latest theoretical simulations from the 1D stellar evolution code Mesa. It will be open source, free, hopefully easy to use, and I really hope it will help make the physics of stars more accessible and understandable. Thank you.
Very cool.
Thank you very much, Eva. That was really, really cool. Okay, great. Let's take questions. Do we have any questions?
Yeah.
Yeah. May I?
Sure.
Eva, this is a wonderful talk. Wonderful work.
Thank you.
I have a very brief remark on in the beginning, the color of stars.
Sure. Yeah.
Colors are something. Colors don't exist. Colors are made in the human brain.
Yes.
Yeah?
Yes.
So, for instance, you say this is the true color how a person would see it when he was close to the star.
Yeah.
If you have an emission nebula, which emits only emission lines in a few elements, the human eye cannot make any color of it.
That's true. I agree.
Always saying this is a true color or a color that the human would perceive. That is only the structure of our eye.
Yeah. Thanks for this remark. Maybe let's make it more clear. So that was probably a simplification, as you pointed out. So I think what is correct to say is that this is a color representation of the effective temperature of the star as seen by the human eye. I think this is correct. Now, of course, stars are something more complex than just this simple circle that I showed. So stars can have all kinds of things around them. Also winds can impact the color of stars. There's all kinds of stuff around them. And as you said, for example, emission nebulae will definitely change what we would perceive as the color of the star. So I think the correct way to phrase this is, this is the way the human eye would perceive the effective temperature of an ideal star. Yeah.
Thank you. Thank you again.
Yeah, sure.
Yeah, follow on that, Eva, because there is something about the colors of black bodies.
Yes.
That always bothered me a bit, and that is, if I take a piece of metal and I put it in a flame.
Yes.
Of the gas stove, right?
Uh-huh.
Then it most definitely doesn't get to 6,000 Kelvin.
Yes.
It gets white at a much lower temperature. And you see red and orange and yellow before that also at much lower temperatures than we usually assign to the effective temperature of stars, which are also basically black bodies, right?
Yeah.
I guess this just amplifies what Hank was already saying. It is something that depends on a lot of things, what you call the color. And stars are just too bloody bright, right? So even a red giant would probably look white to us if you're too close.
Yes, that's true. Yeah.
So, there's more to it than that, and the true color is perhaps a misnomer, right? Because it may not exist, right?
Yeah. No, I totally agree. Yeah.
I agree, Michiel.
Yeah.
Great. Any other questions? Maybe from
I have a question.
TAs?
Okay. I have a question.
Okay.
Do you hear me? I'm Henny. Very nice talk, Eva.
Thanks.
And I like your logo. It's really beautiful.
Thank you. Thank you.
I hope you can put a number of movies on the web, because this is great material for teachers and public talks.
Thank you. Yeah, that's the plan.
Frank is raising his hand.
I had to mute myself. I was wondering, as you're now developing this, do you also have some tips for other people who are maybe developing or thinking of developing Python packages? Like,
in general?
Yeah, just in general, like what are things you ran into and thought like, oh wait, this is something you should think of from the start? Yeah,
so one thing I feel really privileged about is that I took a very advanced Python course online a few years ago. And this gave me very good foundations to be able to do these kind of things. And also I did an internship in ESA where I developed also a web-based application that is based on a Python module. And that really helped me gain experience. So I think I'm already biased in the sense that I have some experience already. So I think one problem that I ran into is this thing that I think everybody runs into, and that's over-optimization from the start. So that means you want to make everything perfect from the start, and you're thinking, oh, I could add this feature and this feature and this feature, and then you never get to anything. So at some point I had to stop myself and just think, okay, what is the most basic thing I can do? Just do that, and then do the next thing that is similar to this. And yeah, so I think one thing to keep in mind, maybe if you want to do this type of coding, is to keep it simple and user-friendly, and keep this guideline throughout, because otherwise you will never ever finish, because there's always things you can do better. So if you just keep to something that is small and working in a simple way, I think it's more useful than if you do the perfect thing that will never finish.
Okay, cool.
I think Sam has a question.
Yeah, it's sort of a stupid thing, but I noticed in the photo at the start of your talk, I don't know if you mentioned this, but the caption of the photo lists the names of the two people, and then just the woman in the photo is just labeled computer. So
yes.
I hope that it's changed recently to
Yeah,
people?
I think it's great that you see this. Not many people notice these type of things, but it's true that a lot of women were involved in the first in solving the first problems of stellar evolution, and I think it's true that their work is absolutely not recognized on many different levels. Like, for example, they don't even mention the name when at the time most of the technical work was actually done by women who were employed and paid a very bad salary, and all the credit went to the men who were at the head of the project and not necessarily doing the actual work. So I think it's good that you noticed this, and I hope that we're moving to an era where this is not an issue any longer, and where every woman will also be mentioned by name and recognized for her work.
Eva?
Yes?
I think that issue was fairly general in the sense that academia was even much more hierarchical. So if you were one of the assistants, it didn't really matter whether you were a man or a woman, your name would just not be mentioned.
Yeah.
Right, but in addition to that, of course, there was a male-female bias in whether you could move up the ranks or not.
Yeah, definitely.
So the women were underrepresented among those who did get credit.
Yeah, I think that's a fair thing to say, yeah.
Yeah, a good example of that is Margaret Burbage, who passed away a few weeks ago.
Yeah.
And whose obituary in the New York Times is actually really interesting.
Yeah, another very good one to read if you want to understand those bits of culture, let's say from the 1940s onwards better, is the autobiography in last year's annual reviews, right? And I keep forgetting her name, that's how bad it is. But basically the woman who was in charge of NASA's astronomy space instrumentation problem and essentially made sure that the Hubble telescope happened.
I think that was Nancy Roman.
Absolutely, yes, Nancy Grace Roman.
I have another comment. May I? The first stellar models were calculated by Martin Schwarzschild.
Yeah.
When on the weekends he was working in Princeton, and on the weekends he could use the computer von Neumann in New York.
Oh yeah.
So he went there every weekend, and then he had to. This was of course not a digital computer, but an analog computer with knobs and things. And every weekend he had to plug in cables all differently. One whole set of cables to calculate the opacity, another set of cables in other holes to calculate the stellar evolution. He never finished in one weekend. So every weekend he went, after he went back, he wrote down exactly how he had cabled it. And then next weekend he came again, started again, and calculated another, what we would now call a subroutine. And in this way he calculated the first stellar model. Really amazing.
Yeah, so much work. And we can just run this in like a minute on a laptop now. It's really amazing. Yeah.
Frank?
Yeah. I also had a question about something related to your output, because you produce these videos, but these videos can often be quite quick.
Yeah.
Then you blink twice and your video is gone. Were you thinking or considering, or because it's something I really like to do, is making it interactive, because you could just make it search through Matplotlib quite easily, that you can just adjust also sorts of knobs and things while you are looking at it. So you could say, I want to look at the elements that are inside my star now, and now I want to know where the heat is produced, and you can see which elements would produce heat. You can flip around between things like that.
Yeah, so the way it's currently set up, this is not going to be possible in a simple way. Okay. But this could certainly be a great idea, a great implementation to try to do this. So the thing that you mentioned earlier, this thing with the time step, that is maybe not the most appropriate one. That is something that is already in the code that you can change. So you can change the time evolution as you wish. And one way that is typically done when you use, for example, Kippenhahn diagrams, is to use a very, very weird unit that is taking the logarithm of the difference between the time and the time on the time at core collapse. So it's basically the time until core collapse, and that is usually for such massive stars, it's a better way to show the passing of time, because it's what it does. It zooms in the later evolutionary stages, which are more quick, but are also more complex and more interesting. So I'm thinking of having just an option that you can just turn this on, and then it's automatically done. But it's already, the way it's set up now, it's already in such a way that you can customize it to any kind of time evolution that you want.
Cool.
Okay, so it's already 1 o'clock, but we'll do one last quick question from Eleanor.
Hi, yeah, really cool talk. So just much more of a practical question about correctly interpreting the tulip diagrams.
Yeah.
So I noticed that these changing compositions kind of sweep out clockwise.
Yeah.
And I just wondered like what the significance of that was, whether it was somehow time dependent or Okay. Maybe I didn't make this very clear because I was rushing a bit through this, but I think it's a very valid point. So why is it going clockwise? The reason is because I'm plotting all the elements counterclockwise. So what does this mean? This means that you know that everything here is a pie chart. So basically the first element is always, and it's always in this order, it's always hydrogen. So the first element that is always plotted is hydrogen, and that will be in the beginning 3/4. So it's not exactly the beginning. You may notice that here there's already a little bit of burning going on. But so basically, in the beginning you have 3/4 of hydrogen, and as you can already see here, this fraction is gonna go down in the center because you're turning some of the hydrogen into helium. Okay, so that means you will have this clockwise motion of the hydrogen becoming, the fraction of hydrogen becoming smaller, so the surface area of hydrogen becoming smaller, and therefore it will move in this fashion, and it will be replaced by helium, and in this case, because it's a massive star, also a little bit of nitrogen, actually, this cyan color. Does that help? Yes, it does. Thank you.
Okay, great. Yeah.
Okay, so thanks again, Eva. That was really great. I've screenshotted all the positive feedback you got in the comment section in case you didn't have time to check it.
Thank you very much.
A final comment. Can you skip a few more slides?
Sure.
One further. Yeah, this one.
Yes.
One back. One back.
One back.
Well, the one with the next one. Next, further. One more. This one.
Yes.
With my color perception, this looks like pizzas.
Yeah. Well, it's good. It's a pizza talk then.
That's right. Thank you.
Okay.
I would ever eat a blue pizza.
Yeah. Yeah, well, you can change the colors if you like and make it more tasty to look at if you like.
Okay, thanks, Eva.
Thank you.
Thank you.
Bye, everybody. See you next week.
Thanks, Eva.
Bye.
Bye all.
Bye-bye. Thank you.
Great talk.